Good morning. My name is George Long, and welcome to Risk Management Professionals webinar series. Jasmine will be in the background making sure that we are operational and also taking any questions. We are using the GoToMeeting webinar interface to support our production, and so if you have any technical issues, please call 877-532-0806, and our staff will be happy to help you out. Also, the PowerPoint screen and my webcam screen can be adjusted by dragging the interface corner to suit your needs for your device. I hope everyone can hear me right now. Let me jump ahead and just let you know that if you do have any questions, there is a chat box down in the bottom corner of the control panel, and so that should be able to allow you to talk directly to our staff. Throughout the webinar, we're going to have you muted, but then at the end, Jasmine will be collecting any questions, and then she'll pass them on to me. We have our question and answer session at that point. Okay, so this presentation is about ignition and deflagrations and detonations of natural gas in pipes and channels. And the reason that this came up as a topic was really because in HAZOPs specifically, but also in any risk assessment, the quality of the analysis is only as good as the team or the individual's ability to accurately characterize the consequence as well as the likelihood that that consequence will occur. And what I noticed is that, attending a lot of HAZOPs, performing a lot of HAZOPs with different teams, that there's a general misconception about if we have a natural gas leak, let's say to atmosphere in unconfined space, confined space, what is the likelihood that we are going to have a detonation versus something like a flash fire? And also, what would the consequences be if we were to have either of those? So this webinar is really an introduction. We're going to talk about the differences between deflagrations and detonations with respect to natural gas. First, more generally, but then we'll actually focus in on what could cause, if we're looking at weak ignition sources, what can cause a deflagration to transition into a detonation and result in the much higher pressures that we will see. If we're looking at pipes, let's say vapor recovery systems, they may be able to handle deflagration pressures just fine, but once we reach detonation, especially around bends and corners or through any obstructions, we may be able to get pipe damage. So the intent here is to discuss, really, to get a nice practical grounding for what we can see with natural gas, which is one of the most insensitive hydrocarbons, or it's the least sensitive hydrocarbon with respect to detonation, so it does have a little bit more confusion there. Okay, so before we get started, though, our company is Risk Management Professionals. We have been helping our clients with process safety and risk management needs since 1995. Some of our key services are listed on this page. And in addition, we have a broad network of affiliates. So if you guys have anything that we may not be able to take care of in-house, we can always make sure that you give us a call so we can find someone that can help you out. Okay, as far as myself, my name is George Long. I'm a senior engineer here at Risk Management Professionals, and I've been doing this for 6 years in the process safety risk management field. My specialty generally is HAZOP and LOPA studies. Just due to the demand, I would say 70+% of my time is spent performing HAZOP studies. However, especially recently, I would say a good chunk of the minority of my time has been either looking at consequence analyses, especially for some marginal applications where we really want to know if a certain setup that requires a deviation is acceptable or not, and then also full-blown QOA assessments. Okay. So the topics covered today, first we'll look at the basics of deflagrations and detonations. Just in general, a little bit. I don't know how much you guys really are interested in going into this, but I have a little YouTube video that we can watch that shows the transition and gives a nice overview. We'll talk about flame propagations. So when we're discussing ignition of natural gas, we're generally discussing a weak ignition source. So to define a weak ignition source, we're saying something that has just enough energy to cause ignition. A strong ignition source would be something that on its own would result in the supersonic flow of the flame front and the detonation. So think of like detonating an explosive charge, right? So that would be a strong ignition source, whereas a weak ignition source could be a spark or something like that, which is what we're more concerned about here. So if we have a spark, how do we get flame propagation, flame acceleration, and then next up, how does that lead to deflagration to detonation transition, or DDT? After that, then we'll jump into specifically the detonability of natural gas and air mixtures. There's a fair amount of experimental evidence that looks at natural gas and air mixtures, specifically related to coal mines and also vapor recovery systems. And so there is, we have a fair amount of not only theoretical but experimental evidence that shows really what components, what characteristics can promote detonability of natural gas air mixtures. Now, because the deflagration to detonation transition is so, it's a series of instabilities, it's not possible to predict with certainty, even using numerical methods, three-dimensional CFD models, within 15 to 20% range as far as when, if we're talking about the run-up from a deflagration to a detonation, where in that range we would actually see that. So after we look at that, some experimental studies have gathered some pressure, velocity, and temperature profiles. So if we were to have a detonation, they were using detonation tubes, so atmospheric pressure and ambient temperature, but what kind of pressures and velocities and temperatures we could see there. And also practical considerations, so what can we take away from this study, and then also safeguards, specifically flame arrestors and detonation arrestors, and how they work to help mitigate this problem. Okay. So first up, we'll discuss deflagrations and detonations. So in an ignition, specifically in a pipe, we're talking about a combustion wave, so we have a reaction front that releases thermal and kinetic energy. And so this diffusion of energy and mass causes the wave to self-propagate. So if we're thinking a channel or a pipe, we're going to have a self-propagating wave. Deflagration is going to be a low subsonic velocity propagating combustion wave. Detonation, on the other hand, would be a supersonic combustion wave. So in a deflagration, we would expect that the reactants and the reaction wave could actually, so let's say we have a wave at a certain subsonic velocity, our pressure waves would be able to interact with the non-reacted gas downstream before the reaction wave meets it, whereas in a detonation, it would be a supersonic wave, and so there would actually be no disturbance of the reactants before. And the YouTube video I have will help show this. Let me switch real quick. Okay. All right. So here, as you can see, first we start off, and to explain this, the bottom row is our velocity, and the second row is our pressure. So you can see the pressure waves, we've transitioned to detonation, which you can see where the flame is by looking at the temperature profile on the third row and also the heat release rate on the first row. So when we're still in the deflagration range, we just had our ignition on the far left side. You can see that we're already getting propagation into the unreacted components downstream. Now, as we continue to follow this, you can see that the temperature and the heat release rate start to speed up with respect to time. So this is stepping through in microseconds. And at a certain point, you're going to see how the all four components start to hit the exact same speed. But right now, so we're still in deflagration regime, and you can see how the pressure waves are affecting the velocity much further downstream of the combustion front than maybe expected just thinking about it. So as we go, here we go. So now we meet detonation. And as you can notice here, there's a run-up distance. So if it's a weak ignition source, we're not going to have immediate detonation. You need some amount of distance for the turbulence, the instabilities, to really feed that reaction front and cause this transition. And in general, the rule is around half the theoretical detonation velocity is where you can start to get like a quasi-detonation regime. But at this point, we're traveling supersonic, and you can see how all of the fronts match up together. So if you keep going on this, then it meets the end. Now, oh, awesome. Okay. So let me go back. All right. Okay. So as I was just saying, in deflagrations, the propagation speed depends not only on the initial state of the mixture. So, if we're looking at methane and air, around 5% to 15%, methane and air will be our flammability limits. And so that will depend also on the size of the confinement. But let's just say, closer to stoichiometric, then the easier we could achieve detonation. But not only this, it's also going to depend on the rear boundary condition, because what you can actually have are these pressure wave reflections that can bounce off of both the front and rear end and then come back and help encourage the instability that the reaction front actually sees as it travels through. So if you have at your ignition source, let's say you have an ignition source at one end and then your wave front travels to the other end of the piece of pipe that's open, well, that closed end will actually be able to reflect the pressure wave and then cause this buildup. And you'll see pressure spikes as well, and you also have transverse pressure waves as the speed increases and you get that compression of the gas as it travels through the pipe. Okay. And so deflagration we can think of as a diffusion wave. So the heat and mass gradient at the flame front is what self-propagates the deflagration. Now, here is another nice little illustration. So here we have an ignition source. We have our flame front. So as the flame front, the reaction causes energy to be released, heat to be released. We get expansion right at that front. And so let's say we had a closed end. Well, our combustion products, so anything to upstream of the flame front, we don't have anywhere to go, right? But let's say we had an open end on that end. Well, in that case, you actually have combustion products flowing against the direction of the flame front. But in this case, you would have the compressed gas pushing the reactants downstream to the unburned gas. You get pressure waves, and as that occurred, instabilities will continue to generate until you reach a point where you transition to detonation. Detonation, on the other hand, so it's a supersonic combustion wave, and you can think of it as a shock wave that is also reacting. It transforms the reactants into the products, and then there's also an energy release. So another way to think about it is you have like a shock front traveling through the pipe, and then behind it is a chemical reaction zone, which can also be described similar to the deflagration zone. However, the strong compression, adiabatic heating of the leading shock is what propagates the ignition. Okay. All right. So the reason that we get this flame acceleration is that self-propagating deflagrations are intrinsically unstable. And there are many different instability mechanisms that all feed off of each other. But as you may have noticed in the YouTube video, the channel was not smooth. They put these little steps. So you get like a forward-facing and reverse-facing step staggered at consistent intervals, which causes the flow regime to destabilize quicker than you would in a smooth tube. And so what you end up seeing is that run-up distances, so the distance between the deflagration from the ignition and the detonation will be shorter as you increase your obstacles and your instabilities due to the flow. So the instabilities, they cause the reaction front to become turbulent, which increases the amount of fuel burned at any given moment. This continues to feed the acceleration, and then depending on if our setup is able to achieve detonation, then it could occur. All right. So the DDT, deflagration to detonation transition. So, like I said, this is affected by boundary conditions. So, how long is our piece of pipe? What's the thickness at the walls? How wide is our radius or our diameter? All of these things can affect it. And so around half of the detonation velocity is what has been shown experimentally to transition from deflagration to detonation in smooth tubes. Instability mechanisms, these can include Landau Dorius, thermal expansion, instability, thermal diffusion, and pressure wave deflections, among many other flow-related instabilities. Okay, so at the onset of detonation, then there are many different theories and methods to achieve detonation. So once we are transitioning in the detonation point, you can get local hotspots or explosion centers. You can also have a pressure pulse or detonation bubbles where you get the transverse waves pressure waves start to form actual bubbles that can then detonate. And there are helical detonations along the surface of the pipe. But because there are so many different ways that we can achieve detonation, it is really not possible to predict if and when DDT will occur. So when you're running like a CFD model, you'll run really a stochastic set of boundary condition and inlet condition or initiated conditions in order to achieve a percentage of the probability for seeing DDT. All right. So unlike DDT, this is direct initiation of detonation. This is where the actual event that causes the ignition is supersonic, allowing for immediate detonation. So then you don't have any deflagration regime. It just immediately starts at supersonic flow. So, for example, explosive charges, they can also use detonation tubes to get a planar detonation from a reflective shock wave that also causes. Some theoretical estimates. So really the first one that you learn about when you're looking at this is the CJ condition, Chapman-Jugot, which assumes that detonation propagates such that the reacting gases reach sonic velocity as the reaction ceases. There's a ZMB detonation model. You can also look at 3D. So that's a one-dimensional model. You can go all the way to like 3D, multi-component, CFD, mathematical models that you can then iterate and solve. But really, for the purposes of matching experimental results to peak pressures, there have been pretty good, at least with natural gas. If you look at like the CJ pressure, CJ velocity, it does match up pretty good, at least with the detonation to experimental models or experimental results that have been seen at the Naval Research Laboratory. Okay. All right, so now we'll jump over to methane and air mixture. So what can influence the detonability of methane-air mixture? Some conditions can include the composition of the mixture. So, if we're at the lean, the rich side, so if we're talking about either like 5% or 15% methane and air mixture, then that's going to be more difficult to achieve detonability than, let's say, right around that 8 to 9% methane and air. Pressure and temperature, and so if we're looking at initial conditions, those will affect it. In fact, they've shown that higher initial temperatures actually increase the run-up distance to go from the deflagration to detonation transition. Also, the size of the confinement. So the smaller the diameter of the pipe or the channel, then the harder it will be to achieve detonation. What they've actually seen is the smallest size, I believe, of pipe that experimentally has resulted in detonation is 1.4 inches, and then the largest is around 41 inches. And at the largest size, really the whole range of flammable concentrations could be detonated. So 5 to 15% they were able to achieve detonation, whereas at the 1.4 inches, you really had to have a metric mixture, and that was it. So you're going to be in a much tighter range the smaller the diameter is. And I have a graph for that in a second. And also the method of detonation initiation. So a strong ignition source is going to promote DDT or detonability much greater than a weak ignition source will. Okay, so as far as methane specifically, and natural gas is, I'm going to interchangeably say methane and natural gas. But in most experimental studies, they did use natural gas. They didn't use the exact same compositions. It's a wide range, so you do get some variance in the results because of that. And so the first thing we'll look at is, how does the natural gas itself, the composition of the natural gas itself, affect the ability to detonate? And before we jump to that, though, there's no confirmed reports of a self-supported detonation in an unconfined natural gas and air mixture. So they've done experiments, we'll have an unconfined cloud. They'll use a high explosive charge, and really the pressure waves decay. There's no self-sustained detonation once that initial initiation event decays. And so you need, at least with methane and air, you need some kind of confinement in order to achieve those detonation pressures. Okay. However, that does not mean that detonations cannot occur, and so that's really the misconception. DET has been shown experimentally, theoretically, in smooth and obstructed channels. Also, let's say you were to use a more sensitive gas mixture. Sometimes they'll use like a hydrogen-oxygen mixture to start the detonation, and then it can promote the DDT and methane and air. And like I said, so the smallest tube diameter is 1.4 inches. So even small diameter piping could be susceptible to DDT. And especially, if the run-up distance for small diameter piping is on the order of around 5 to 10 diameters. And so we're only talking, a couple of feet that would be enough, even in a smooth channel, to see this detonation. Okay. So here's the detonability limits, and this was taken from a Naval Research Laboratory report, and it compiled a lot of the different experimental studies and then also the theoretical best fit curve for those. As you can see, that as you reach, so the left-hand side is 1 over diameter. As you reach the peak, then that's the smallest diameter, which is right around at 1.4 inches. And that also requires the tightest concentration of methane in air to achieve detonation. And then as you get wider in the channel, it really reaches the point where anywhere in the flammable range in methane and air, you could also see detonation. However, for smaller channels, even if you're in the flammability range, you may not be in the detonation range. So that's something to think about. Okay. As far as natural gas composition, it can range from 82 to around 99% methane by volume. It includes ethane, propane, and higher hydrocarbons. Carbon dioxide, nitrogen may be present, and this all introduces uncertainty into the detonability of a natural gas for a specific facility or system. Some studies have looked at specifically ethane concentration, and they've seen that a high ethane content will bring down that initiation energy to achieve detonation. So you could have 2 different experiments running side by side. They have 2 different sources of methane or of natural gas, and they could have totally different results. So it's something to think about. That in a study, in a controlled experiment, you may see that the minimum diameter is 1.4 inches for achieving DDT in pipes, but for a specific facility, you could have a range of compositions of natural gas, and so we don't want to say that definitely any 1 1/4 inch and below pipes are okay. We don't have to worry about this problem because we don't know yet, really. Okay. All right, so some observations. A weak ignition source will not cause a detonation of an unconfined natural gas in air cloud. But in channels, really anywhere from 1 point something inches all the way up to the 41 inches, So this is the gas explosion test facility that the Navy Research Laboratory hosted. Any range you could achieve detonation with a weak ignition source, depending on the composition of the natural gas and the distance, the run-up distance, and also the boundary conditions for the channel. You could get that. And so for smoother channels, things that have less methods of invoking turbulence, you're going to need longer run-up lengths, so you're going to need more time for that deflagration to transition to detonation than you would if there were more obstructions in the pipe or channel. Okay. Some variables to look at. So these are all atmospheric pressure and ambient temperature as the initial pressure and temperature for these studies, and they were able to see for natural gas and air detonations 1,400, 1,800 meters per second flame velocities. Pressures. So this is an atmospheric detonation tube. So they have one closed in, one opened in. And they got over 250 psi, and then also temperatures up to 3,500 Fahrenheit. So 250 psi may not sound like a lot if we're looking at carbon steel piping. You guys aren't too worried about it, depending on what you are using. But pressure wave reflections, like we talked about, let's say you have an ignition source, and now you have a closed end away from the ignition source. Here you can get these reflections that can cause instantaneous localized pressures that can peak at 2 to 5 times the pressures that are just quoted here. So instead of 200, 250 psi, you could have instantaneous pressure of 500, even to over 1,000 psi. So definitely at that point, you would be worried about potentially damaging piping. Some other practical considerations. So if we have a detonation combustion wave traveling through pipe, it's going to have a lot of mass, a lot of momentum, and anything that can change that direction could potentially be damaged. So even if the pipe can withstand the pressures, 250 psi pressures, pipe ends, shut-off valves, blower housings, or even the flame arrestors themselves could be damaged by the momentum pressure of the wave. Another thing to think about are, in your facility, what are your ignition sources? Here we talk about static discharge. We could have sparks by, let's say the blower and power. It's the housing, pilot flames, or even the main burner flame. You could have flashback back into, let's say, your vapor combustor system. Also, low energy versus high energy. So high energy, we're talking about something that on its own could result in the detonation. So things like for a typical facility, lightning, a heater burner, like a heater box explosion, vessel explosion, things like that would be what we're looking at with high energy. So really we're more worried about that low energy ignition ramping up to causing the detonation. And also let's say you do have some, a lot of the times when you do have like a pipe failure due to this, the incident investigation will typically find that there has been multiple events where this has occurred, and it slowly weakens the integrity of your system before you finally have that failure. All right. Okay. So here we have flame arrestors and detonation flame arrestors. So what do we want to do to stop our self-propagating wave? And here, so if we're looking at a deflagration, it's going to be subsonic, and so we have that diffusion of heat and mass that propagates it. So what we want to do is we want to take away as much heat as possible, and so that the flame will stop propagating. So here, what you see is you can use a nice heat-conductive material, and you want as much surface area as you can. So you have a bunch of little channels, and you can see in the picture. So you send a flame through all of these corrugated metal channels, and then that should help to remove that heat and then stop the flame. You also would like to have some kind of a temperature shut-off for your system upstream of that. So once the flame reaches a detonation arrestor or the flame arrestor, that high temperature will also initiate safe shutdown of your system. So the difference between a flame arrestor and a detonation flame arrestor, so all that additional momentum and heat that we talked about with detonations that can compromise the integrity of the system. So that can also, damage a traditional flame arrestor. So you can buy a flame arrestor for any type of system, and the detonation flame arrestors are designed to handle that additional load. All right. All right. So that actually went a lot quicker than I was expecting, but we're up to the end. So here are some of our upcoming webinars and conferences, and then also we'll do our question and answer session. So any questions you guys might have, be happy to take. So let's see if Jasmine has gotten any questions. And if this is something that you guys found interesting and you'd like to go in a little more detail, at this point, I really didn't think I was going to have enough time, but what I wanted to do as well, and I'll do it in a separate webinar, is discuss, okay, so now that we know the difference between our deflagrations and detonations with methane or natural gas, let's talk about how to actually characterize the consequence levels. So we're going to look, if you have a certain flow rate, composition, and expected event, so if we're looking at like a flash fire or a detonation, how do we actually come up with the values for what pressures we should see, what kind of thermal radiation effects we could have, and how these could impact nearby receptors like people. And so, we can look at things like thermal dose of a person, so our thermal radiation over time. We can also look at, pressures, peak pressures inside of pipes to actually determine, within, 15 to 20% range, what kind of pressures we could see if this is going to damage our piping or equipment, and also if we would expect some kind of potential shrapnel or any kind of loss of containment and personnel impact. All right, well, thank you guys very much for attending the webinar. It was my pleasure to talk with you. And also, if you guys do end up having any questions later, you can always email me or RMP staff. My email is george.long@rmpcorp.com. It's been a pleasure. Thanks, everyone.